Welcome to our talk. This presentation will cover our survey on research related to the provenance analysis in visualization. The survey is a joint effort by many authors, and the presentation will also be covered by a few authors. What is provenance? The Oxford Dictionary defines provenance as a place of origin or earliest known history of something. This is often used in the context of a valued object or work of art, such as a famous painting. For a painting, its provenance includes information such as who the author is, when and where it was painted, and the history of ownership changes. The concept of provenance is adopted and extended in computer science and applied to notions such as data, computation, and user interactions. For example, the provenance of data or data provenance includes the context information such as how, when, why data are collected, recorded, stored, and processed. It provides a broader context than how it was originally used, not only the information to repeat the process, but also context such as why it was done. Why do we need this survey? Provenance is a fast-growing area in the visualization research. Recently, there are many new works that relate to theories on visualization and interaction provenance, provenance capture and visualization, and provenance analysis. Such analysis can be used to understand users, for example, for evaluating visual analytic tools, and support user sense-making tasks, such as providing personalization and helping collaboration. Actually, there is so much new work that in this survey we can only focus on the last part, which is an analysis of provenance.
In this survey, we focus on the analysis of user interactions and provenance data in the field of visualization, whose main purpose is similar to the meta-analysis as defined by Reagan. As such, we only include existing work that incorporates meta-analysis based on user-generated interaction provenance data with a high-level goal of improving, enhancing, or understanding a visual analysis system, visualization process, or visual artifact. We define only recorded information of an interactive visual analysis session without any further analysis out of scope. Also, sophisticated machine learning or active learning approaches based on binary decisions are not within our scope because they do not take the meta-analysis into account. We also do not include user studies that collect user-generated data and work on collaborative sense-making if there is no additional analysis of the provenance information beyond recording and sharing. We started by collecting existing work that we know from our previous research. We continued with a systematic approach by manually screening all issues from 4 journals and all proceedings from 5 conferences or symposia over the last 11 years, starting in 2009 and ending in 2019. For a systematic approach for our paper collection, we continued with a 3-stage process for the tagging. We first started with an explorative tagging with literature we were aware of. Each contributor of this contribution was assigned to at least one conference or journal to screen. The used tags were manually assigned to get an overview of relevant literature. This process resulted in a collection of 266 papers. The aim of the second round of coding was to unify the categories and narrow down the scope. That is why the second stage is called categorical tagging. To achieve this, we developed a closed set of keywords for the spectrum of possible reasons for doing meta-analysis on provenance data, as well as for the state-of-the-art of user interaction analysis. Each paper was coded by at least 2 co-authors independently. All co-authors were in constant exchange to resolve cases for an ambiguous and uncertain classification. In the last stage, Supplementary tagging, we decided to further split up the two main categories, the why and how, into subcategories. Therefore, we divided the collection into 6 subcategories for the why aspect and 5 subcategories for the how. In the course of the analysis, we came to the conclusion that exclusively tagging the how section for provenance analytics is not sufficient. To address this issue, we introduced an additional what aspect that allowed us to characterize the different encodings of provenance data in more detail. After going through all 3 phases, we ended up with 105 papers. We collected all papers and displayed them in a static table in our paper. The categories are highlighted in the respective color for why to analyze provenance data in green, what types of provenance data and ways to encode it in brown, and how to analyze provenance data in blue. Finding an appropriate structure for the table was difficult. We decided, therefore, to let users explore the list of publications interactively. We implemented a website where users first get an overview of the categories and then can decide whether the why, the how, or the what has a higher priority in search.
The structure of our survey is based on a high-level provenance analysis model that we created to describe the important factors and their internal relationships in provenance analytics. Analysis goals are the reasons for provenance analysis and give rise to requirements such as what data capture and how the data is encoded. In our case, we call it the what. Encoded provenance data is then further evaluated by analysis techniques, how, such as classification models or probabilistic models. At the end of this process, users gain either user-specific or system-specific knowledge that can be used to improve or adapt any of the process model components to enhance the overall provenance analysis iteratively.
There are many reasons why researchers and practitioners analyze provenance data. We highlight 6 common categories in the paper. We begin with understanding the user. Here, the goal is to create theoretical and computational models that describe the reasoning process. Examples include quantifying hover and click patterns, predicting personality traits, uncovering exploration bias, and modeling attention. Also common was the analysis of provenance data to understand the system itself or to evaluate its usefulness. These include papers on using mouse and eye data to learn the importance of visual elements, modeling task performance to guide system design, and visual analytic systems to evaluate interactive visualizations. Perhaps the most common goal that we observed was in the area of adaptive systems. The aim here is to improve the usability and performance of visualization tools, and topics ranged from recommended systems, providing guidance to the user, and adaptive prefetching. Another category that we observed was model steering, and here researchers use provenance data to improve the underlying data representations or the machine learning models. This category includes systems such as ForceFire that uses semantic interaction, and dysfunction that uses direct manipulation to adjust the projection calculations for high-dimensional data space. We found a series of work aimed at replication, verification, and reapplication. For instance, with VizTrails, an analyst can create, edit, and compare provenance data flows. Harvest recommends notes and relevant views based on previous analyses. Knowledge Pearls allows users to rank and retrieve previous visualization states. Finally, researchers have analyzed provenance data with the goal of report generation and storytelling. We found papers on producing automated annotations, data-driven reports, and summary insights.
In this section, we will briefly discuss the types of provenance data and how to encode them. We divided existing work into 4 types: sequence, grammar, model, and graph. Sequence is probably the easiest way to log activities. One of the most common activities is user interactions, which includes keyboard input and mouse movement. Logging of application state happens when the user's interactions are not semantically meaningful. For example, user interactions for web browser are simple, say mouse click, but logging the pages that the user has visited, also known as clickstream data, results in much richer representation of a user's behaviors. There is an increasing interest in logging a user's mental state, often with the use of physiological sensing, for example, EEG. Instead of logging individual user interactions, such as button click, higher-level semantics can be recorded to provide semantically richer provenance, for example, using the interaction taxonomy by Jing Song-yi and others. Similar to logging application state, in visualization, a user's browsing behavior in a large 2D canvas can be recorded based on what parts of the canvas they are viewing. This type of logging is often applied to map visualization. A user's interaction can be treated as a continuous stream of events. As such, temporal data analysis methods can be applied to find patterns. The second type is grammar, which encodes user interactions as logical rules. Each user's interaction results in a predicate. For example, x is greater than 10. These interactions are chained together using first-order logic. More complicated is the use of a domain-specific language or script. For example, in Wrangler by Kendall and colleagues, a user's interactions for data cleaning are represented as script that resembles regular expressions. Another similar approach is to convert a user's interaction into a specification or template. The third type is model. For example, if a user's interaction results in the refinement of a machine learning model, the log can be the changes to the parameters of the machine learning model. In contrast, where the system wants to infer something about the user, for example, in a mixed initiative system, then the logging would be the gradual learning of a user model. The last type is graph. Provenance information is often used for sense-making, and the user's knowledge can be represented as knowledge graph, entity graph, or concept graph. Another type of graph is an interaction history graph. This is related to logging raw user interactions, but with additional analysis to discover more structure. For example, a user performing an undo operation would result in a branch behavior in a graph.
Next, we consider techniques for the analysis of provenance data. The categories that we present in our survey are not clear-cut. Indeed, there is a considerable amount of overlap between the various provenance analysis techniques we see here. The most common technique is the use of classification and statistical modeling to differentiate sequences of user actions. Here, we see a variety of classification techniques that include common strategies like clustering to permit users to interact with eye gaze patterns, as well as regression, used to predict the user's skill acquisition when interacting with bar graphs. Common machine learning techniques like support vector machines have been used to process and classify eye gaze data. Further, topic modeling and other dimensionality reduction techniques have been used to identify relationships between users and movie recommendations, for example. More complex techniques have also been seen, like artificial neural networks used to predict important regions in an interface, as well as hierarchical techniques like decision trees. Other techniques that focus on patterns in the data can be divided into those that either automate the analysis of those patterns of provenance data or permit users to explore and analyze such patterns manually. With respect to automated analysis, techniques such as adaptive contextualization can compute metrics based on a user's provenance data, while visualization-centric approaches to clustering and pattern matching on collections of websites enable the detection of branching patterns in event sequences. Similarly, notes and concepts that log past analyses can be retrieved using systems like Harvest. In the manual analysis context, sketches are a common technique for analyzing provenance data, allowing users to query, for example, trajectory information. In addition, rule-based systems permit users to generate rules, encoding events automatically in regular expression queries. Probabilistic models can be used to support the nuance and uncertainty inherent to interpreting and inferring from imprecise provenance data. Basic statistical techniques like the t-distribution and chi-squared distribution enable the clustering of groups of users. Bayesian classifiers, simple probabilistic classifiers that incorporate independence assumptions between features, can also be used to identify data items from large datasets that are of potential interest to users. Fuzzy classification results like those generated by convolutional neural networks predict tasks as next actions. Markov models are also commonly used to perform such actions as anticipating mouse interactions during exploratory data analysis. Additionally, natural language interfaces can be used to interpret the complex instructions provided by. Program synthesis represents another method for provenance analysis, closely related to the grammar approach of encoding provenance data. For example, the use of domain-specific languages to encode provenance data, which later may be converted into regular expressions. More complex forms of encoding, like graphs, have also been used for the encoding and analysis of provenance data. Additionally, understanding the cognitive behavior and strategy of users via think-aloud studies and the review of interaction logs can enable the post-hoc analysis of provenance data for tasks such as analyzing eye movement data to identify user exploration strategies. Further, interaction can be used to analyze provenance data. The semantic interaction approach used for interaction with the projection of glyphs and the manipulation of constraints and coordinates demonstrate one means of interactive exploration to understand underlying models and learning routines. With respect to visual analytics in general, the Inside Insights system, among others, provide web-based interfaces for the analysis and exploration of provenance data. Additionally, knowledge graphs have been constructed for the purpose of collaborative analysis. Finally, the generation and analysis of visual design can be used to develop methodologies for participatory design processes and formative evaluation strategies, later used for the design of novel analytical tools.
The last part will briefly discuss research opportunities in this area. There are still many unsolved problems related to user cases discussed earlier. For example, user intent modeling is an important challenge that is far from resolved, and a fully automated solution is unlikely in the near future. Provenance can be beneficial to related fields such as machine learning. One example is explainable AI. By capturing and visualizing the evolution of the internal structure and how the model responds to different inputs, the user can have an improved understanding of model behavior. As for provenance encoding, many of the existing methods do not fully consider the multi-layer nature of provenance, from the low-level system logs, such as mouse movement, to the reasoning-related provenance, such as insight and rationale. Besides increased complexity, it is difficult to capture provenance such as user thinking. In most cases, this is still done manually, which is ineffective and time-consuming. In terms of provenance analysis, many of the existing works still rely on the relatively simple techniques such as k-means clustering, and new techniques from fields like machine learning are likely to further improve performance. There are still many fundamental problems that await better solutions. One such example is provenance chunking, which groups the steps in an interaction sequence based on the analysis actions that they belong to. Chunking closely related to the multi-layer issue discussed in the What section and help connect provenance across layers. Most of the techniques and tools reviewed here have specially designed provenance format. However, real-world analysis often involves integrating provenance data from multiple tools, which is currently not possible unless there is a common standard. This will be a challenging task, but essential and beneficial to the entire field and the wider research community, encouraging new collaborations and enabling new research.